We are now beginning the next major phase of this class, talking about something called a vector valued function. A vector valued function is what we call a function which produces vectors. Specifically, a function which takes in a single input, often referred to as t, and based on that value of t, produces a vector of outputs. A vector that might have a form like x as a function of t, y as a function of t, and maybe if you're in three-dimensional space, also z as a function of t. So you have a list of multiple outputs in a vector. This is a vector-valued function. Now, vector-valued functions can be used to represent lots of different things in the real world. The first major use of vector-valued functions is to represent the position of an object that's moving through two- or three-dimensional space over time. In this situation, the output vector, the output of your vector-valued function, is being used to point to the object's location in space at a specific moment in time, t. Let me give you an example of what I mean. Someone says, I have an object who is moving through two-dimensional space. The position of this moving object will be indicated by this vector-valued function. At any given moment in time t, this vector is going to point to the object's location in two-dimensional space. So let's try and describe and sketch and understand how the object is moving based upon this formula. I'm going to create a little table with several t values from my domain. So I'm dealing with t values that are between 0 and 1 in this problem. So I'll throw down some values of t like 0, 0.25, 0.5, 0.75, and 1. I'll plug all of those into my vector valued function to figure out where the function is pointing, the location to which the function is pointing at each of these given moments in time. So for example, when t is equal to 0, if I take that t value and I plug it in to this function, the result of plugging that t value into this function is the vector 1 from 1 minus 0 and 0 from 2 times 0. So at this particular moment in time, this vector is pointing from the origin to the point 1, 0. So this says, hey, at time t equals 0, the object's position is right here. I'm pointing to this location at this moment. So this is where the object is located at this moment. Let me also go ahead and plug in t equals 1, the final time in my domain. So when t is equal to 1 and I plug that into my formula, I get 1 minus 1, giving me 0 here, and I get 2 times 1, giving me 2 for a y component. So that vector is pointing 2 units straight up. Your object's position is right here. The vector is pointing to the object's location at that moment. You can repeat this process for the other values of t that we've used in our table. For example, when t is equal to 2.5, we get 0.75 and we get half. When t is equal to 1/2, we get 0.5, 1. When t is equal to 0.75, we get 0.75 and 1.5. So if I draw those vectors in the xy plane from the origin, they're pointing to these 3 locations in space. They're pointing right here when t is equal to 0.25. They're pointing to this location when t is equal to 0.5. And they're pointing to this location when t is equal to 0.75. So based on that scratch work, let's see if we can understand and describe what the object is actually doing and how it's moving between these two moments of time. It looks to me, based on the pattern of the dots, that this object is traveling in a straight line between these moments. So the path of motion I will draw here below is from this point where x is equal to 1 up to this point where y is equal to 2. The object is traveling from this position at the initial time along a straight line path toward this position at the final time. So I will draw that straight line and I will add some arrows here to indicate how that object is moving as time moves forward. So I could say, for example, in a English description, object is moving in a straight line from the point 1, 0 toward the point 0, 2. That would be the movement described by this vector valued function. Straight line movement from this initial point to this final point. So here's this situation as represented on GeoGebra. Here in blue is the sketch of the straight line that the object is traveling along. And here this black vector is the vector r of t, which is pointing from the origin to some location on the curve. As we vary the values of t from 0 to 1, we see that vector pointing to different positions on the curve. So the object is following this straight line over time from this initial position to this final position. Let's do another example to see how different functions can give rise to other shapes. For example, supposing that the object's movement is being represented by this vector valued function, where the x is determined by cosine of t and the y is determined by sine of t. Let's go ahead and describe the object's motion if its position is being represented by this function. You may actually be able to predict, just based on the nature of the functions in the components here, what shape is going to be formed. But you can always just plot some points. Now, there's no domain restriction in this problem that I have to consider. So I might just throw down some values of t that seem convenient based upon the functions that I'm given here. So something like t equals 0, t equals pi over 2, t equals pi, 3 pi over 2, and 2 pi. These are pretty convenient inputs for trig functions like sine and cosine. So when t is 0, our output vector is pointing 1 unit directly to the right, 1 produced by cosine, 0 produced by sine. When the angle is pi over 2, sine and cosine are producing 0 from cos and 1 from sine. When t is equal to pi, cosine produces -1 and sine produces 0. When t is equal to 3 pi over 2, cosine produces 0 and sine produces -1. And then by the time t returns to a value of 2 pi, we're back in the positive x direction. So to represent this situation in a picture, we'll start with some scratch work. When t is equal to 0, there is a vector pointing to the object's location from the origin, 1 unit directly to the right. So that tells me, hey, the object is right here at this position on the positive x-axis when t is equal to 0. When the time has increased to pi over 2 units, the vector valued function is now pointing to a location 1 unit straight up on the y-axis. So that's saying to me, hey, your object is right here, 1 unit straight up on the y-axis, when the t is equal to pi over 2. Then when t is equal to pi, my vector is saying, hey, your object is over here on the negative x-axis. That's where it is when t is pi. And then when t is equal to 3 pi half, my vector is pointing straight down. So that's where my object is at this moment. And then by the time t increases to 2 pi, we're back here on the positive x-axis. From these points we've plotted, and by thinking about what sine and cosine are doing, we probably have enough information to predict the nature of the path of motion. What we have here is an object that's moving around in a circle. The object is moving around a circle of radius 1. Specifically, it's moving around the circle counterclockwise. So this would be the path of motion, and I could describe it as the object is moving counterclockwise around a circle of radius 1. So once again, we can visualize the situation on GeoGebra. Here in black is a vector that's pointing from the origin to the object's current position. And as time goes along, we see that vector pointing to different locations on this circle of radius 1. The second major use of a vector-valued function is to represent vector quantities that might be changing over time. So for example, here we might be dealing with a moving object whose velocity can change over time. So I can use a vector valued function to represent that changing velocity. For example, and we'll talk more about this in a later lesson, I claim that for this object above, this guy here who was moving in a circle counterclockwise over time, the velocity of this object at any given moment is given by this function. The velocity of the object at time t is given by negative sine in the x component and positive cosine in the y component. So let's go ahead and calculate this velocity vector at a couple of different moments in time, and let's draw those velocity vectors on the path of movement. So setting up a table with the same sort of convenient values of t as before, 0, pi over 2, 3 pi over 2, and 2 pi. Now let's see what the velocity is doing at each of these moments. When I plug these t values into my velocity function, when t is equal to 0, I get this vector 0, 1, a velocity vector that's pointing straight up. Now, let's recall that at time t equals 0, the object's actual position was over here on the right side, and then the object's velocity vector at that instant is pointing 1 unit straight up. So from that, I know that the object's direction of motion at that instant was upward, which makes sense based on the picture. At that instant, that object was moving upward. And I also know that at this instant, the object was moving with a speed of 1 unit, because the speed is the velocity's magnitude. If I consider another moment in time, such as pi over 2, and I plug that into my velocity function, I can see what the object's velocity was at this later instant. If I plug that in, sine is producing -1, and cosine is producing 0. And in the picture, if I remember that at time pi over 2, my object was here at the top of the circle, if I draw the object's velocity at that same moment when it was in that location, we see that velocity vector pointing to the left, verifying what we would expect, that when the object is in this exact position, at that exact moment in time, the object is traveling to the left in that instant. Here is a recreation of the situation on GeoGebra. The blue circle is the object's path of motion, and the green vector is the object's velocity at the relevant moment in time. And as time moves along and the object is traveling to different locations on the circle, we can see an interesting graphical phenomenon, which is that the velocity vector is at all times tangent to the path of motion. The velocity vector is always tangent to the path of motion. And as we study velocity in more detail in later lessons, we'll see that that phenomenon occurs no matter what path of motion you're dealing with. The velocity vector is always tangent to the path. So that's the second major category of uses of vector valued functions. Vector valued functions can be used to represent vector quantities that change over time. So if you have an object with a velocity that's changing over time, or if you have an acceleration that's changing over time, or if you have a displacement that's changing over time, or if you have a force that's changing over time, you can represent all those situations using a vector valued function. So the last major category of uses for vector valued functions is that they give us a really nice way to represent curves within a computer. So perhaps some of you have used a curve tool in a program like Illustrator or Blender or SolidWorks, or even something as simple as Paint. If you use the curve tool in one of these programs, then you can extend the curve and you can bend it and you can reshape it to form whatever kind of look you're going for. And different programs will give you different ways to control or reshape the curve in question. Editor Sam, if you could please go ahead and show the people what this looks like on Krita, for example. If you could also show the people what this looks like on Blender when you're doing a Bezier curve or when you're doing a NURBS curve on Blender. If Editor Sam is doing her job, then you should be able to see that depending upon what specific program you're using, they give you a couple of different ways to control the shape of the curve that you're trying to generate. So a pretty interesting question in computer graphics is how do you determine what the curve should be based upon the control points or the handles that you've given the user to draw the curve? That is a very, very interesting and complicated question. But in the end, when the computer calculates and generates the curve that you want to draw, the curve is represented in the computer as a vector valued function. And when we're thinking about the vector valued function that represents a certain curve, we're thinking about that function the same way we did here in part 1. The outputs of the vector valued function point to different locations on the curve as we plug in different t values. The only difference between those is that when you're dealing with position, t represents an actual time, whereas when you're representing a curve mathematically, there's no sense of time here, right? This is just a shape. And so in this context, the input t represents just an abstract input or an abstract parameter rather than time. That concludes today's video. A vector valued function is a function whose outputs are vectors. A function that takes a single input in and produces a list of outputs in vector format, an x of t, a y of t, and potentially a z of t. Vector valued functions have several uses, the first of which is to represent positions of moving objects. When you have a vector valued function that's being used in this way, the input of the vector is time, and the output is pointing to the location of the object in space at that moment in time. The second major use of vector valued functions is to represent changing vector quantities, such as a velocity that changes over time or a force that changes over time. And the third major application of vector valued functions is as a computer-friendly way to represent digital curves in, for example, digital art or in AutoCAD drawing softwares like SolidWorks.